Alright, in this lesson we are going to continue our work on graphing rational functions like these, but we're going to include vertical asymptotes, horizontal asymptotes, slant asymptotes, holes, and we're going to talk about whether or not functions are continuous, discontinuous, and whether or not those discontinuities are removable or non-removable. So there's a lot of vocabulary that we're going to cover in addition to graphing the rational functions. So, buckle up. Alright, looking at problem number 1, if I want to know what the vertical asymptotes are, I look at the denominator. And I'm going to need to factor this to see what the vertical asymptote is, or there could be more than one. But before I start factoring, let's actually go ahead and talk about the horizontal asymptote first, because it's easier to see when it's not factored. So for the horizontal asymptote, that's the one where it's all about the degree. So it depends. If the degree of the numerator is less than the denominator, the asymptote is y equals 0. If the degrees are equal, then the horizontal asymptote is a over c, leading coefficient over leading coefficient. And if the degree of the numerator is greater, then there is no horizontal asymptote. So for this problem, we have degree 2 and degree 2. So since they are the same, this is the situation where we make the horizontal asymptote out of the leading coefficients, 1 over 1. So that's why the horizontal asymptote will be y equals 1. And make sure you include the y equals part, don't just put 1. Alright, so you can't have a horizontal asymptote and a slant asymptote, so there won't be a slant asymptote. Alright, slant asymptote will occur if the top degree is 1 higher than the bottom. So that's not happening, so there is no slant asymptote. So now let's talk about vertical asymptotes and holes. For that, we're going to need to factor these two polynomials in the numerator and the denominator. So let's see. So we've got f of x equals. So as we factor this, looking at the numerator, x squared is surely x times x. 6. Well, 6 is either going to be 2 times 3, or it's going to be 1 times 6. Alright, looking at the middle, it's probably going to be 2 times 3. Alright, remember, inner plus outer must equal the middle. Alright, the middle that we're shooting for is a positive 1. Inner, we have 2x. Outer, we have 3x. I can get a positive 1 out of this if I do a positive 3 and a negative 2. So there's my positive 3 and there's my negative 2. Also, that will give me negative 6, because negative 2 times positive 3 is negative 6. So that's how you factor the numerator. Alright, now for the denominator, same type of thing, should be pretty easy. Again, x squared can only be x times x. 10 will either be 2 times 5 or 1 times 10. Alright, looking at the middle, it's probably going to be 2 times 5. Again, inner plus outer must equal middle. Inner, I have 2x. Outer, I have 5x. So I'm trying to get a middle of 3x. I can get 3x if I have a negative 2x and a positive 5x. So there's my negative 2, and here's my positive 5. Also, that gives me negative 10, because a negative times a positive is a negative. Okay? Now, I'm looking at these factors in the denominator as I'm thinking about the vertical asymptotes. But first, I have to ask myself if anything is going to cancel out. Because if any of these factors cancel out, they won't be vertical asymptotes, they will give me holes. So in fact, I see that I have an x minus 2 in the numerator and denominator. So those are going to cancel out. Alright, so I'm going to get a whole from this. Alright, when these factors cancel out, that's where wholes come from. Alright, now, and I'm going to get my vertical asymptote will come from the x plus 5. So let's do those two things. So if I set the x plus 5 equal to 0, that will give me my vertical asymptote. So if I go x plus 5 equals 0, subtracting 5 from both sides gives me x equals negative 5. So that's my vertical asymptote. X equals negative 5. Again, don't forget the x equals part. You can't just put negative 5. Now, if I set this equal to 0, the x minus 2, that's going to give me the x value of my whole. Alright, so so if I add 2 to both sides, that gives me x equals 2. Alright, that tells me that I'm going to have a whole at the point 2 comma something. I need the y value though, alright, because I want an ordered pair for this whole. Now, if I want to find the y value that goes with this, then I'm going to use my calculator to find it, but I'm going to be careful to only type in this part of the function. Alright? Not the whole function. Otherwise, I'll just get an error at 2, which is why there's a hole there in the first place. You can't have 2, because 2 minus 2 is 0, and then I have a 0 in the denominator, so I can't put the whole function in. But if I put in this part that doesn't cancel, that will help me find the y value. So let's do that. X plus 3 over x plus 5. Let's table it up. Okay, so x plus 3 over x plus 5. Alright, and I wanted to know about the value 2. So I might as well go ahead and put 2 right now. Okay, so at 2, the y value is 5/7. Okay, so I have 2 comma 5/7. Okay, which by the way, for graphing purposes, it would be helpful to have a decimal, so I'll toggle it, and I see that that is about 0.7. Okay, so I'm just going to put a little note to myself that this is approximately 0.7. Okay, now let's graph the stuff that we have here so far. Alright, so we have a vertical asymptote at -5 and a horizontal asymptote at 1. Let's graph that. Okay, so my asymptotes are like this. Also, let's go ahead and graph this hole. So I have, I'm going to have a hole at 2 comma 0.7. The hole is a single point that's not included in the function. So let's graph that as an open circle. So 2 comma 0.7. Alright, so if I go over 2 and up 0.7, that's going to be pretty close to the line. Alright, so I'll put an open circle up there. So there's my hole. Okay, so at this point it would be a good time to go ahead and get some points going. Let's look at a table of values and get the graph going. So you know, I really can just continue to use this, keeping an eye on my vertical asymptote. Let's get a couple points to the left and a couple points to the right. So for example, let's look at -7 and -6, for example. Let's check that out. So if I go over to -7, alright, at -7 I'm at 2. Okay, so -7 comma 2, I'm right there. Alright, at -6 I'm at 3, so that's right there. Alright, I always like to look at the decimal to the left and right of an asymptote. So I'm going to look at negative 5.5 to see what's going on there. To do that, I'm going to just quickly switch to ask mode so I can just ask directly what I want. So what did I say I wanted? Negative 5.5. Okay, let me move this over a bit. Okay, so negative 5.5. Alright, so at negative 5.5 we have a value of 5. So here I am, negative 5.5, and I'll have a value of 5. Okay, so those 3 points give me a pretty good idea of what's going on here. So I can go ahead and draw this branch now. Okay, now let's go ahead and draw this branch, which is I'm sure doing this type of thing based on the fact that there's a hole right there. But again, I like to do decimals on both sides of the asymptote. So I'm going to do negative 4.5 now. Okay, so negative 4.5. So that's negative 3. So at negative 4.5, I'm at negative 3. So that'll be right there. And then I'll just go ahead and do negative 4 and negative 3. Okay, so let's see. So negative 4. At negative 4, I'm looking at negative 1. So it's going to be right here. And how about negative 3? Alright, at negative 3, I'm at 0. So negative 3, comma 0. And then the whole also counts. So that certainly shows me what this graph is going to be looking like. It's going to be this type of thing. And it's going to go right up to that hole. I'm going to skip over it. Okay, so this is what your graph is going to be looking like. So let's go ahead and do the domain. You should be able to tell me the domain immediately, or once you see what the vertical asymptotes are. You should be able to say the domain just from that alone, even without the graph. Okay, because the domain going from left to right is always going to be, for example, negative infinity to asymptote, and then asymptote to positive infinity. Okay, so negative infinity to negative 5, union 5 to infinity. Okay, because we're going left to right. So we'll just write that down. So negative infinity to negative 5, union negative 5 to positive infinity. Okay, and we didn't even need the graph for that. As soon as you see the vertical asymptote, you know that the x values will work that way. From the left, got to skip it, and then you go to the right. Wait a minute. I lied a little bit. We have to make sure that we also leave the hole out of the domain. Okay, so that was almost a mistake on my part. So it's not, I misspoke when I said you could just do the domain just from the vertical asymptote. You also have to make sure you're skipping the hole as well. Okay, so I'm going to have 3 pieces to my domain. So let me just, let me move this up a little bit. Okay, so I am still going to have negative infinity to negative 5. All right, this piece is still there. But over here, I'm going to have to divide my domain into 2 pieces. So it'll be negative 5 to 2, and then 2 to infinity. So I'm going to have 3 pieces to this. So instead of having negative 5 to infinity, I'm going to say negative 5 to 2, and then union 2 to positive infinity. Okay, so basically you're going to wind up treating that hole just like another vertical asymptote, even though it's just a single point discontinuity. Alright, and yeah, let's talk about continuous and discontinuous. Alright, a function is continuous if it is unbroken like this. If you could just trace your pencil along the function from one end to the other without picking your pencil up, then it's continuous. If the function graph is broken into parts, then that's discontinuous. If there's any sort of a gap or hole, it's discontinuous. So first of all, looking at this function, is this continuous or discontinuous? Well, this is certainly discontinuous. If you think about it, I have three pieces here. I've got these two branches, but even this branch over here has two parts to it because I've got this point discontinuity right here. So it's definitely not continuous, so I'm not going to check that box. So it's discontinuous. Now we have to be more specific. So here are three ways that a graph can be discontinuous. If there's an asymptote, we call that an infinite discontinuity, and that's non-removable. If you have a jump in the graph, right, that's a jump discontinuity, and that's also non-removable. If you have a hole in the graph, that's called a point discontinuity, and that is removable. Okay, so here we have, well, you know what, okay, the way I have this set up, it's like we're supposed to choose between removable, and we have both, okay? It's definitely discontinuous, but we have a removable, okay, is the point discontinuity. And we also have the non-removable, so maybe I'll just label this like the point 2 comma, what was it, 2 comma 5 over 7, that's the removable discontinuity. And we also have a non-removable discontinuity, and that's the asymptote. Okay, well, I guess the asymptotes. X equals -5 and y equals 1. Those are non-removable discontinuities. Alright, and that is it for problem number 1. I went into a lot of detail there, hoping that because we have so many problems to do today, 8 of them, I'm hoping we can do the other problems faster. But yeah, I'm stopping this video here because it's already 18 minutes long. So I will see you on the next video.